Assalamualaikum. My name is Ahmad Firdaus bin Badrul Hisham. My metric number is S760099. So for my part, I will present about question 1. Okay, so for question 1A, by typing in the coding into MATLAB, you will get a graph which is the discrete time cosine signal x1. And then for question B, the length of the signal is 61. And then for question C, to determine whether x1n is periodic, we can use the equation omega over 2 pi equals to k over n, where omega is 0.3 pi. Substituting the value, we will get 3 over 20 equals to k over n. Since 3 over 20 is a rational number, the signal x1 is periodic. The fundamental period is 20 samples. For question 1D, by typing in the coding that we have created into MATLAB, we will get the second signal, x2. And using the subplot command, we can see the two graphs in one page. And then for question 1E, to determine whether x2 is periodic, we can use the same equation. And by substituting the value, we will get 11 over 100 equals to k over n. Since 11 over 100 is a rational number, the signal x2 is periodic. The fundamental period is n equals to 100 samples. And the difference between the two graphs, by the frequency x1 oscillate faster than x2, and x1 completes a full pattern every 20 samples, whereas x2 completes its fundamental pattern over 100 samples. And for shapes, the x2 reach a higher amplitudes than x1, and additionally, because of the different phase offset, the initial shape of the wave at n equals to 0 start at different point in their respective cosine cycle.
Assalamualaikum, my name is Muhammad Imam Zaini. So today I will present the MATLAB implementation to generate and plot the depth complex sinusoidal signal xt equal 5e equals E0.3t, E equals J60 for the time range of 0 to 6 seconds. Okay, this is my answer. So in the code, I define the amplitude as 5, the decay rate alpha as 0.3, and the regular frequency 6. The secret then extract the real, imaginary magnitude and phase component of the signal. So the figure 1, the real part blue start at 5 and the imaginary part red start at 0. Both show decaying sinusoidal oscillation that get tighter due to the height frequency. So next, the figure 2, the green curve show the magnitude decay is exponentially from 5 towards 0, while the magenta plot show the phase warping between negative pi and positive pi radians, creating the smoke pattern. So this is all from me. Thank you.
Assalamualaikum, my name Muhammad Khairul Naim bin Abdul Halim, metric number S47691. I will present question 3 for our MATLAB assignment. These are 3 signals in question given. In question A, we define the range from the negative C until positive C. This slide show the plot of Hn, H1n, H2n, and Xn. For H1n, we clearly see the 3 impulse. For H2n, the signal alternate between positive and negative value because the negative exponential base. And for Sn, the amplitude decrease and the n increase because the base in 1/2. In question B, the slide show the plot of for Vn and Yn. The convolution operation combine the effect of the input signal and the system response. As a result, the output signal become the longer and sharp change. In question C, we reserve the order of the system. Now the input signal first pass to the H2 and the intermediate output become the Vn equal to Xn multiplied by H2n. Then the signal convert with Hy to product the final signal. For the question D, here we compare the new Vn and Yn. We observe the intermediate signal Vn in the question B is different compared to the question C because the input passed through a different system first. However, the final output Yn remain the same.
My name is Wong Kar Wei and I will present the question 4. For For the answer of the question 4a, got three figures. The first figure is input signal XD, and the peak is between the 0 and 5. For the second figure is input response HD. The peak is nearly to the 0, and the third figure is convolution output. That means the yt equal to xd multiplies hd. That means the first two figure multiply and become the convolution output, and the peak is between the 0 and 5. For the answer of question 4b, first we need to do the convolution integral and find the answer is yt equal to integrate upper limit negative and lower limit negative infinity try times t minus 2 over 3 times e times power negative t minus t sine times t minus t times u times t negative times t minus t times dt. And the triangular signal exists only for negative 1 lower than or same t lower than or same 5. And the u times t minus t and will becomes the t lower than or same t, and it will becomes the negative 1 lower than or same t lower than or same mean minus 5 or t. And the yt equal to integrate upper limit mean 5t lower limit negative 1 times 1 minus t minus 2 over 3 times e power negative t minus t sine times t minus t times dt. The that was got two region. The first region is negative 1 lower than t and lower than 2, and we will get the xt equal to t plus 1 over 3. For the region 2 is 2 lower than t lower than 5, and the xt will become the 5 minus t over 3. And the final answer is yt equal to integrate upper limit 2 lower limit negative 1 t plus 1 over 3 e power negative t minus t sine times t minus t times dt plus integrate upper limit 5 lower limit 2 5 minus t over 3 times e power negative t minus t sine times t minus t times dt. For the answer of question 4c, um, the analytical result and MATLAB numerical convolution should produce nearly identical waveform. Small difference may occur because MATLAB uses numerical approximation. The time step dt equal to 0.01 introduce discretization error. Convolution in MATLAB is simple rather than continuous. As dt becomes smaller, the MATLAB result becomes closer to the analytical solution. Effect of the triangular signal xt. The triangular signal is infinite in duration. It smooths the output waveform. The peak occurs near the center of the triangle. Effect of ht equal to e minus t sine tut. The exponential terms cause decays. The sine terms introduce oscillation. The unit step makes the system causal. The convolution output behaves like a wait and delay oscillatory response of the triangular pulse.
Okay, I will continue. So this is my question 5. So Today we using the MATLAB to analyze an ideal linear phase low pass filter with a cut-off frequency of WC equal to 2 and a time delay of 3 seconds. Part A, we find the impulse response HT by the inverse Fourier transform. Plotting this in MATLAB show a classic sine function centered and peaking at the time delay t equal to 3. Then the part B, we introduce the input signal xt equal sine 4t because this input has a wider backward. Then our low pass filter cut off the highest frequency, and then the output by t plot here show a small time shifty version of the original signal. This is the answer for the question 5b using the MATLAB. You can see the part B for the input signal and part B output signal. For the part C, we approximate a periodic square wave using a Fourier series sum of up to 20 harmony. Pressing this through our filter remove the sharp edge and high order harmony. So result in smooth delay sinusoidal like output wave. Thank you. And the last for the question 5C, this is the answer for the using for the MATLAB 5C. So part C, this is a square wave input S, and the part C, the last is filter output signal. Thank you.
For the question C, given the transfer function and use the MATLAB commands such as TF, ZPK, pull, 0 and ZPZmap to analyze the system. For question 6a, we define the zeros, pulse and gain. 0 are at -2 and 1, pulse at -4, -1 and 2, gain is 3. Then we convert the model into transfer function form and plot the pull 0 map. From the MATLAB output, the system has one pull at S equal to 2, which lies in the right half plane. Therefore, the system is not stable. For the question C, use the residual function in the MATLAB to perform partial fraction expression. From the result, we obtain residual value of the 18 per 5, 2 per 3 and 89 per 15.
The answer of question 6C, first we need to find the derived transfer function. The function is y triple prime t plus 7 y double prime t plus 16 y prime t equal to xt plus 12 yt. Y triple prime plus 7 y double prime plus 16 y prime minus 12y equal to xt. Sys plus 7s square ys plus 6s ys minus 12ys equal to xs. Xs times s cubed plus 7s square plus 16s minus 12 equal to xs, and the xx equal to 1 over s cubed plus 7s square plus 16s minus 12. And this is the code that has been run out on question 6C in the MATLAB. For this figure, it is an answer that after we run the coding in the MATLAB.